In the second video for the introduction into rate laws, I will be solving for the value, the numerical value, and the units of the rate constant, which is the lowercase k, that is in the rate law itself. Remember that it's a rate constant that's only constant for a reaction, meaning this reaction that I'm looking at right here, at a temperature, which means maybe, let's say, 25. And then the units that you're going to be deriving are based off of the order overall for your rate law. So be careful that the rate constant is probably the least constant we kind of have in chemistry. All right, so before we can do K, we do have to solve for the rate law itself. And in the previous video, I determined how the order with respect to nitrogen dioxide was 2, and the order with respect to carbon monoxide was 0. So if you didn't catch that, you can watch the other video that I have made before this one. The other thing is be very careful of the rate units. They can be moles per liter per second, but they can also be really any amount per volume per time. All right, so how do you solve then for your rate constant? And you can pick any trial, or you could do all 4, but realistically, if the experiment is done well, you should be able to pick any trial, and you should get the same rate constant for each one. If not, you can do all 4 and then average it. So what I'm saying is you could find the rate constant for trial 1, trial 2, trial 3, and trial 4, and then you could, if you wanted to, you could take all of those and then average them. But typically, you're going to get the rate constant will be close enough that you could just pick any trial. So what I'm going to do is I'm just going to pick trial 4 because I didn't use that one yet. And what I'm going to do is just substitute in the numbers off the table. So what I mean by that is you just pull off the concentrations that are there and the rate of that trial. So for example, since that rate was 0.033 and that was moles per liter per second, I just took the molarity and divided that out. We do not know what K is. That's going to be our unknown. And then we don't put NO2, we'd put the actual concentration that allowed us to get this rate. And then squared, because again, in the last video, we found out that there was a squaring effect, or it was second order with respect to NO2. And then we found out that it was 0 order with respect to the carbon monoxide. Now, the other thing that's going to be important is that we do put the units in here. So on the next step down, what I'm going to do is put in the units besides. So this is the rate, and then this is K. And then it's going to be 0.4 squared, but it's also going to be molarity squared. So moles squared, and then liters squared. I'm just going to kind of put that all in parentheses. And then it's just going to be 0.10, which would be moles over liter. But then this is going to be all to, if you push this through with all of them, they will all be zeros. So in the end, all of those will be gone. And you'll have rate equals 0.033 moles per liter per second. And then you're going to have 0.4 squared. I'm not going to solve for that. You can just put that in your calculator. And then moles squared over liters squared. And then I'm just going to stay kind of on this same page. So I'm going to end up kind of deleting the above part here, right here. And then I'm just going to slide this up. It's right there. And then what I'm going to do is move the units around and the numbers. I'm actually going to solve numerically last. So I'm going to have 0.033 moles, and then liters, and then second. And then I want K to be isolated on the one side by itself. So I'm going to have then the inverse, liters squared, 0.4, keep that one in parentheses though, squared, and then moles squared. And then that's going to equal this rate constant, lowercase k. You're going to have an uppercase k when you have equilibrium constant. So this is a lowercase k. And then I'm just going to use kind of like a highlighter here to get rid of some of the values. So your liter here will change to just being 1 liter in the numerator, and then mole will be in the denominator. And then numerically, what you're left with is 0.033 divided by 0.4 squared. And then that's going to be the units. And I'll just kind of pull the units over here. I'm just going to slide this whole thing up a little bit here. Just so that this isn't on that line. And then we're going to have liter left in the numerator, mole left in the denominator, and then second also left in the denominator. And then that's going to be K. And I want to kind of solve for this in 2 separate steps. This part will equal 0.21, so there's like your numerical value for K. And then the units of K are liters per mole per second. Now, the other thing you can do is write this as 0.21 liters mole to the -1 second to the -1. And then you might also see that somebody may take this and just say it's 0.21 molarity -1, meaning like the inverse of molarity, and then per second, seconds to the -1. So you might see that as a unit also. And then that is what our K value is. And that is our rate constant for this reaction, this one reaction, at this one temperature. And so you've solved for what's called the rate constant. But again, it's unique for the nitrogen dioxide reacting with carbon monoxide. Let's kind of zoom all the way out here. Creating these 2 products. And then this would be the rate constant that you solve for in the units. Now, I just want to kind of sneak down here. This was actually on the other video. This is how I solve for the orders of the 2 reactions, or reactants, I should say, for the reaction. So that was in the separate video that was before this one. This one is just basically trying to solve for the value of K. Now, we technically solve for it for this one. And you could do this for all 4 trials, but they tend to be the same number if it's like a book type problem. So you don't usually have to find all 4 of them and then average. All right, well, hopefully that would help you solve for, again, the value and the units of K.